So I just want to start by thanking the NSTF for putting together this event. I'm very excited to present to you my presentation on tackling climate challenges with quantum computing. So just a bit about me. My name is Shivani. I'm a PhD candidate in computer science at the University of KwaZulu-Natal. I'm also the CEO and co-founder of Fraqtal Technologies. As a researcher, my interests focus on the intersection between quantum computing and machine learning. Specifically, I am interested in how quantum computers can enhance AI methods and how AI in turn can be applied to solve problems in quantum computing. Fractal Technologies is a deep tech company that I co-founded with Mr. Ian Joel David, who I think is also in the Zoom meeting. And we are a deep tech company that offers AI and quantum-powered solutions to businesses. I'm also the developer of PinKit, which is an open source Python package for solving differential equations with physics-informed neural networks. And basically, these methods provide a powerful alternative approach to traditional numerical approaches for solving differential equations. Traditional numerical approaches being finite difference methods and finite element schemes. But with physics-informed neural networks, what we do is we have the output of the neural network representing an approximate solution to a differential equation. And then the parameters of the network are then optimized such that this approximate solution satisfies the differential equation. And unlike traditional approaches, physics-informed neural networks do not require costly evaluations on fine grids. And a very cool aspect to them is that they can incorporate experimental data as well, which is very necessary in the modern challenges that we have today, where we often want to incorporate some data that we've collected from sensors or through studies, and we want to incorporate that with mathematical models that we have. But above all, I am someone who cares deeply about the world that we live in and the world that we're leaving behind, which is, again, why I'm very excited to talk to you about climate change and how quantum computing can maybe aid us in this battle. So climate change is the defining problem of our century. And this problem refers to the long-term shifts in the Earth's average temperatures and weather patterns. So there are natural processes that can influence the climate, as we know, but there's this really rapid warming that's happening today, and this is being driven primarily by human activity. And the human activity I'm referring to is the burning of coal, oil, and gas. And basically, the burning of these natural resources release greenhouse gases into the atmosphere. And this traps heat in the atmosphere and causes the planet to warm faster. And the rate that it's warming is faster than ever before. And the result of climate change is that we experience more extreme weather, we have rising sea levels, we have melting ice caps, which leads to shifts in ecosystems, and all of these changes in the world puts an increase of pressure on our food, water, and energy systems. And what we're seeing is that every major sector, whether it's energy, agriculture, transport, finance, health, all of these sectors are being reshaped by these climate impacts. And climate change is really going to impact so many of our lives in the future. So I've identified a few what I call climate challenges. And these are basically problems that I think we need to solve in order to either understand climate change, combat the effects of climate change, or prevent climate change itself. So I'm going to delve into each of these challenges in more detail, but basically I want to focus on climate modeling as a challenge, predicting extreme weather events, and reducing our energy consumption. So I'm going to go through each of these challenges in more detail and talk about why they're so important, and also what are the challenges that we are currently facing with classical computing methods. So climate modeling involves the simulating of physical processes. And these physical processes that are relevant to us govern the atmosphere and oceans. And these, being able to simulate these processes helps us understand global climate dynamics. So practically, climate modeling involves solving a set of or sets of nonlinear partial differential equations, like the infamous Navier-Stokes equations. And I say infamous because these equations are notoriously difficult to solve. And these equations basically describe the nonlinear evolution of fluids. And the reason why they're so difficult to solve is the nonlinearity adds a layer of complexity. But the nonlinear evolution also leads to turbulence, and simulating turbulence requires high performance computing, really, really powerful computers. So, why should we care about climate modeling? Well, finding accurate solutions to equations, which is the goal of climate modeling, allows us to make predictions using mathematical models. And this is important because we can have an equation that will govern how the temperature or the air pressure or whatever quantity we're interested in, how those quantities will change. But we may not be able to use those mathematical models to make actual predictions. We need to solve them first. And once we have our predictions, we can predict how global temperatures will change, sea levels will change, and how there will be shifts in regional climate patterns. And these predictions are going to be essential for informing national and international policy, as well as informing our infrastructure planning, which is going to be very important in this age of climate change. So, what are the challenges with climate change? Well, a very big challenge is grid resolution limits. So basically, to make these equations solvable on classical computers, what we do is we have a domain over which we solve our equations, and we divide our domain into a coarse grid. So if we were to divide the Earth into a coarse grid, we may end up with, 100 kilometer squares. And these are basically not small enough to capture small scale effects and small scale physics, like, for example, cloud formation. So we only have access to, or we can only work with really coarse grids. But as I mentioned, they do not help us understand what happens on the smaller scale. So you may ask, okay, if we need finer grids, if we need to divide our domain into finer grids, why not just use finer grids? Well, the problem with that is that when we improve the grid resolution, this requires more computational power. And this is where the challenge of computational cost comes in. And at some point, we may reach a limit to the classical computing power that we have access to, even if we parallelize the tasks. The other challenge in climate modeling is, as I mentioned a few minutes ago, the nonlinearity in the equations. And basically, nonlinear differential equations are much more difficult to solve than linear differential equations. And this has to do with the fact that the variables interact in more complex ways. So we can't break down our problem into smaller, simpler parts that can be solved individually. And another challenge that the nonlinearity introduces is that our solutions are highly sensitive to initial conditions. So even small data errors can cascade into massive prediction inaccuracies over time. So the next climate challenge I want to speak about is predicting extreme weather events. And this basically means to forecast specific high impact meteorological events such as hurricanes, heat waves, or heavy precipitation that could lead to, for example, flooding. And this challenge basically requires the rapid assimilation of real-time satellite data and sensor data. And it could also involve using equations. But basically, we want to be able to predict the trajectory and intensity of dynamic weather systems. So we want to be able to predict when, for example, a forest fire will happen, or a flood will occur, or there'll be like an extreme heat wave, so that we can inform people and we can plan for these events. And I'm sure you can kind of guess why this is important. Well, it's for disaster risk reduction. So we want to be able to know when these extreme events are going to happen so that we can inform people, they can be prepared, we can put certain infrastructure or have people in place to help with these disasters. And having these predictions will allow us to enable timely evacuation procedures, for example, the optimized deployment of emergency resources and emergency personnel. and it will also help protect critical infrastructure during these extreme conditions. What are the challenges with predicting extreme weather events? Well, one of the challenges is time constraints. So basically, this is a time critical problem, but the amount of data that we need to analyze is so vast, and the simulations that we need to run are so complex that sometimes we struggle to make these predictions fast enough to basically allow us to take actionable actions before the event occurs. The other challenge is in the processing of large data sets. So typically, we gather a lot of data from satellites, sensors, maybe data from simulations, and processing all of this data requires a lot of compute power. And as I mentioned before, there may at some point be a limit to the compute power that we have access to classically. Um, the other challenge is ensemble limitations. So basically, what meteorologists do is they run multiple simulations, which we call ensembles, and each of these simulations are run with slight variations. But basically, the classical computing power that we have access to limits the number of these simulations that we can perform. And this increases the risk of failing to predict low probability, high impact outlier scenarios. Because things like heavy precipitation, heat waves, forest fires, for example, are low probability events, we need to be able to account for many different scenarios, which means running many different simulations. The other important climate challenge I wanted to speak about was reducing energy consumption. So, the way that I see it, this challenge is twofold. We want to develop materials that make energy storage or industrial production processes more efficient. And we also want to address the growing energy footprint of high performance computing itself. So, why is this problem important? Well, basically, industrial processes like fertilizer production, for example, and data centers are major global energy consumers. I'm sure we all have heard statistics about how much energy it requires to make a query to a large language model, for example. Um, but there are other expensive processes, like, for example, the production of fertilizer. And the production of fertilizer specifically consumes approximately 1 to 2% of the world's total energy supply. And data centers alone also consume about 1.5% of the world's total energy or electricity demand. And there is a direct causal link between energy use and climate change, because as I mentioned right at the beginning of this presentation, the more energy that we consume, the more greenhouse gas we produce. And this basically accelerates global warming. And these kind of statistics about the energy that we require are quite concerning because what we're experiencing is also an AI and a technological boom. And basically, we can predict that we're going to need many more data centers going forward. And the amount of electricity that all of these data centers are going to consume is going to be really large. And this is not just a problem with AI, even if you're just running a chemical simulation, for example, which is important in fields like drug discovery. These simulations require high performance computers, which in turn requires a lot of energy. And this is a problem. The challenges when it comes to reducing the energy consumption, if we look at the problems that we've addressed, is that there is a growing demand for compute power. So, as I mentioned, the one that everyone is thinking about is running these AI models or training these AI models. But there are other fields that also require simulation of complex processes that also benefit from the power of supercomputers. So, there's this growing demand for compute power. The other challenge is material or chemical simulation limits. So, if we want to design new catalysts, for example, this requires simulating complex chemical reactions. And these simulations require resources that scale exponentially on classical hardware. And basically, this prevents the discovery of energy efficient catalysts or materials. The other issue that we have is power constraints. So a top tier supercomputer runs on about 20 megawatts, which is about 20 million joules per second of power. And this is equivalent to the total, this is the statistic that I was sure everyone had heard of, but a supercomputer basically requires the same amount of energy as a small city. And so that's, 20 megawatts is enough energy to power about 20,000 homes. And to make this even more frightening, because of this growing demand and because of the success that we've seen with supercomputers and with, just throwing more compute power at problems, the next generation of supercomputers are going to be bigger, better, and they're going to require even more power. So we really need to think about how we can either reduce our reliance on classical supercomputers or how we can run them more efficiently. Okay, so onto the main topic of today, which is how quantum computing can be applied to this problem. Just a quick introduction to quantum computing. Quantum computing is an entirely new computing paradigm. It's an entirely new model of computing itself. And basically, the kind of key distinction between classical computing and quantum computing is a few things. And, we have the basic unit of information on a classical computer being the bit. On a quantum computer, we have a qubit. A qubit has a state, and the state of a system of qubits can be evolved by unitary transformations. And the other distinction between classical computing and quantum computing is that when we use quantum computers, we have to perform some measurement at the end of our evolution or processing. And the measurement is what basically obtains information from the system. And this is how all quantum algorithms work. Essentially, we have our qubits, which are initialized in some state. This will store the information that we want to process. We process the information through some evolution. We evolve the quantum state, and that is processing the information. And then we measure to obtain the information that we want to. If that's too much detail, I just wanted to introduce the terms that I'm going to be using when I talk about the quantum algorithms going forward. And as mentioned in the previous talks, the future of computing is hybrid. It's not, we have classical computers now, and then in the future, we're going to have quantum computers, and these are going to replace classical computers. That's not the case. Instead, we only want to use quantum computers for the tasks that they are good at. And this is very similar to how we have GPUs and TPUs, which have been designed for very specific tasks and we only use them for very specific tasks. So, for example, we would use a GPU to train a machine learning model or perform inference with a machine learning model, or to game to render really high quality graphics. But you don't kick on your GPU every time you just send an email. But for that, you would use the CPU. So similarly, what we want to do as researchers is identify what tasks quantum computers are really good at or really efficient at. And so far, we know that they're good for certain linear algebra tasks, for example. And we would only want to use the quantum computers for those tasks, not to run an operating system, for example. But yeah, this kind of hybrid view is already being used if you consider the use of GPUs and TPUs. But in the future, we want to add quantum processing units to the wheelhouse, basically, or the toolbox of computing. So now I want to talk about how quantum computers can tackle each of the challenges that I've introduced. And the first challenge I want to speak about is climate modeling with quantum computers. And basically, this requires quantum algorithms for solving nonlinear partial differential equations. And this sounds simple enough, right? Develop quantum algorithms for solving nonlinear differential equations. And there are already a wide range of algorithms for solving linear differential equations on quantum computers. But the problem is that specifically solving nonlinear differential equations with quantum computers is a much more challenging task, just as solving nonlinear differential equations is more challenging, even for classical computers because it requires numerical methods. It's the same thing here. And the challenge with solving nonlinear differential equations is that we have to represent the solution of our differential equation as a quantum state. And we can only evolve the state with unitary operations according to the Schrödinger equation. And the Schrödinger equation is a linear equation. So to realize the required nonlinear evolution, we need to implement non-unitary evolution steps. And this requires using more complicated projective measurements or open quantum system dynamics. So it's not very easy to do on a quantum computer. But there are approaches that have been developed. And I think you will see at the bottom of the slide, there's a paper that provides a very nice review of all the algorithms that are being used, or all the algorithms that have been developed for this task of solving nonlinear partial differential equations. And I just want to highlight two important methods or two important kind of categories of methods. And the first one is the linearization-based quantum algorithms. So basically, given a system of nonlinear differential equations, we first linearize the system using something like Kalman linearization. And then we solve the system using existing quantum linear system solving algorithms. So the key thing here is that we have to perform some linearization first, and then we use a quantum linear ODE solver, for example. And the specific algorithm that is often used is the HHL algorithm. And yeah, you can read more about this in the paper that I've put at the bottom. So the next important class of algorithms I want to talk about for this task is hybrid quantum classical algorithms. So basically, given a system of nonlinear differential equations, we want to first represent a trial solution as the output, so trial or approximate solution as the output of a parameterized quantum circuit. We then use a classical computer to optimize the parameters in the circuit. And we optimize the parameters to minimize a loss function that basically will tell us how well the trial solution or the approximate solution obeys the differential equation. So basically, this it's hybrid because part of the algorithm requires a classical computer and part of it requires a quantum computer, and it uses something called parameterized quantum circuits. And this is very similar to the classical physics-informed neural network approach, except the difference here is that the neural network is replaced by a parameterized quantum circuit. But the idea is essentially the same. And I just wanted to highlight an example of where this method was used, specifically in the context of climate or weather modeling. And that is in this paper, Potential of Quantum Scientific Machine Learning Applied to Weather Modeling. And basically, in this work, the authors used a hybrid quantum classical algorithm to solve the barotropic vorticity equation, which is basically what they use as a simplified model of the atmosphere. And they performed a simulation or simulations using this algorithm. And in those simulations, they found that the quantum model achieved high accuracies. So this is a big step forward in using quantum computers for climate modeling. The other challenge that I think quantum computers could really address is predicting extreme weather events. So, classical machine learning has already been applied to the problem of detecting, for example, wildfires from images, detecting floods, maybe from images or other hydrological data. And what we can do is basically just use the quantum analogs to these classical machine learning methods and apply them to the exact same problem. So, for example, we already have quantum convolutional neural networks and we have recurrent neural networks. quantum recurrent neural networks, and we can use the quantum convolutional neural networks to detect wildfires in images. We can use the quantum recurrent neural networks to predict rainfall as a time series. And in this paper, I've basically shown, in this paper, what the authors have done is they've used classical and quantum machine learning models to predict floods. And the data that they used was historical river and meteorological data, including rainfall measurements, river discharge rates, and past flood events, which served as, I guess, the label in this learning problem. And they basically, given these conditions, classified the conditions as flood or no flood. And a number of different quantum machine learning methods achieved high accuracies for this task, including the quantum support vector machine and the quantum enhanced decision tree. And the quantum support vector machine basically requires executing the kernels that are going to be used in the support vector machine on a quantum computer. And this is a very well-established method in quantum machine learning. So the other challenge that can be solved with quantum computers is reducing energy consumption. There is a really interesting and powerful quantum algorithm that could help reduce our energy consumption for fertilizer production, which is a problem that I mentioned earlier. And this is the algorithm I want to highlight to solve this challenge. But first, let's talk about the problem. So currently, the industrial process to convert nitrogen into ammonia for fertilizer requires very high temperatures and high pressures. So as you can imagine, it's very, very energy intensive. In contrast, naturally, we have bacteria that use the enzyme nitrogenase to perform the exact same reaction at room temperature and standard pressure. But the problem is that classical methods prohibit us from understanding how this reaction occurs. So we don't yet understand how the active site of this nitrogenase enzyme actually breaks down the bond so efficiently and converts the nitrogen into ammonia. But if we could understand how this happens, then we could design a catalyst that achieves the same thing, and mimic the biological process that would require a lot less energy because it doesn't need high temperatures and high pressures. It requires at room temperature and standard pressure. And this algorithm has been developed in this paper, elucidating reaction mechanisms on quantum computers. And in this paper, they basically developed a quantum algorithm to solve this problem. So they demonstrated that quantum computers can actually reveal the reaction mechanism of nitrogen fixation that happens at the active site of this enzyme. And they achieved this by calculating reliable activation energies. And this is the bottleneck or the problem that traditional quantum chemical methods cannot solve. And they also conducted a resource analysis and estimated that a quantum computer with only around 111 logical qubits could perform the necessary simulation. So this is a very cool example of a quantum algorithm where we have a useful advantage, but also a practical advantage in the sense that it can actually be run on a manageable, a quantum computer with a manageable number of qubits. So, just quickly, I just want to discuss the limitations because what I've introduced is how quantum computers can tackle these different climate challenges. But there are limitations involved with, or limitations with regards to using quantum computers for this task. And there are basically significant engineering and theoretical hurdles that we need to cross before there's this widespread use of quantum computers for these tasks. And the limitations include hardware limitations. So as it was mentioned in the previous talk, we still have relatively small quantum computers that are prone to noise. And for every logical qubit that we need in the algorithms that we design, we need many, many more physical qubits to actually execute the algorithms. And basically, what this means is that we need devices that are less prone to noise And we need devices that are much larger than what we have today. So this is an example of an engineering hurdle that needs to be crossed on the hardware side. There's also this data loading bottleneck. So as I mentioned before, these when you solve these climate problems or you have the problem of predicting extreme weather events, typically you have data from many different sources and really massive data sets. And encoding classical data into a quantum state is a non-trivial problem. Currently, it's a significant bottleneck in our quantum machine learning algorithms. So we still need to find an efficient way to actually load the data from the classical data that we want to process onto a quantum computer. The other problem or the limitation is a quantum advantage. So we basically need to prove utility. We do a lot of research that shows that certain algorithms can be executed on a quantum computer. But the problem is that we don't just want the algorithm to be possible. We want it to be faster or more efficient than an algorithm we would run on a classical supercomputer. So we're still searching for algorithms that have a proven practical speed up for important tasks. The other problem is verification. So if a quantum computer solves a complex nonlinear differential equation that a classical computer can't solve, how do we actually check the answer? So we basically need to develop new methods that that have proven advantages in solving the problem so that we can verify that the output is correct without relying on a classical machine to actually validate the answer. So these are the limitations, but there's a lot of research being done, and I see a lot of promise in this field for tackling climate challenges. So yeah, thank you. Does anyone have any questions?
Shivani, that was extremely interesting. I
Thank
wish we
you.
could spend the day discussing all of this, um, particularly because you are looking at tackling the climate crisis. And this is indeed where we are, is we need to understand more, and the Earth is a complex system which we
Mm,
cannot understand with classical computer power.
mm,
Um, so this is absolutely on topic, relevant, up to date. The other day we had a discussion forum on climate change, actually, climate change, environment, water, and food challenges with the science councils. And so we have been immersing ourselves in this area once again. And there's a lot of progress in terms of what is understood about
mhm,
the Earth and the connections among these factors. But oh gosh, we're just scraping the surface. It
mhm,
needs to be more and faster and by yesterday.
mhm, mhm.
Thank you very
Definitely,
much, Shivani.
definitely. Sure.
Um, Sibusisiwe, you've got your hand up.
Yeah, sorry, because I couldn't type on the Q&A section. Thanks, Shivani. Very interesting presentation. The one question I was thinking about when you highlighted the problem around data loading bottlenecks
Mm,
specifically, because you tend to find this not only in terms of the climate data, but generally with your images, with your gene expression information, etc.
yeah.
What are some of the approaches that you are looking at or think are most kind of like most well positioned to
Mm.
explore to address this specific problem?
So I think with the data loading problem, a kind of, and I don't know if this is a cheating way to get around it, but if you actually assume the fact that you start out with some quantum data, then the data loading is no longer a problem because basically, but this is if you don't use classical if you're not interested in classical information, but you have the information coming from some kind of quantum experiment that you run, and then thereafter you process it, then you benefit from the gains of the quantum algorithm that you process it with, but you don't have to account for loading the data first. So I think that is, if we can find algorithms that are useful in that context, that would be very, very important. But there are other algorithms that are being developed, like divide and conquer strategies that perform the same kind of state preparation. But yeah, it is a significant challenge. But I do think that the kind of key application that we should start looking at is when you have some kind of quantum data, and then the algorithm is just processing that thereafter.
Very interesting.
Thank you.
One of the things
Very
that
much.
we've tried to get around the problem has been some kind of sampling strategy. But you can imagine there, the challenge is you obviously, you're getting a sample of your data set, so you're not utilizing the benefit of your full data set at any single instance of running a pipeline. So I was just interested in just sharing, what are you looking at when it comes to that particular challenge? Yeah.
Thank you very much for that question. Sibasiwe. I better say Dr. Makanya.
It's fine. Everybody
Thank you
calls.
for that question and that interaction. Thank you, Shivani.
Yes, thank
We're
you.
moving
I'll
on.
just answer the other question in a typed form.
Okay, thank you so much.
Okay.